Hello and welcome to today's webinar organised by Waters. My name is James Strachan, editor of the Analytical Scientist, and I'm delighted to be the moderator of today's event, which will discuss pushing the boundaries of science with multi-reflecting time-of-flight technology. The Waters team will introduce the new Waters Xevo MRT mass spectrometer and how its combination of high mass resolving power and mass accuracy can be achieved independently of the acquisition rate, delivering performance at speed. The first of our three speakers today is Jane Kirk, Principal Consulting Product Manager at Waters. Jane has over 18 years' experience in LC-MS instrumentation, technologies, and software. Graduated from York University with a PhD in analytical chemistry and has previously held several scientific roles at Waters, developing applications and supporting customers. Passion for translating technical information into impactful scientific messaging was the driving force behind Jane's move into marketing. Our second speaker is Jason Wildgoose, who is a Senior Principal Consulting Technical and Engineering Lead for Discovery, Characterization and Imaging, also at Waters. Jason joined Waters in early 1997, straight from university, as a test and installation engineer, working on the original QTOF product. After 3 years, he moved into research and development, continuing to work on time-of-flight developments, as well as adjacent technologies such as ion guides, detectors, and ion mobility. Jason stayed in MS research for 18 years and ultimately assumed responsibility for time-of-flight design and development. In 2018, he joined the newly formed Advanced Mass Spec Technologies Group, focusing on innovation and new technologies, where he acted as a technical lead before transitioning into his current role. In addition to the Waters team, we are delighted to be joined by our third speaker, Professor Perdita Buran. Perdita is Chair of Mass Spectrometry in the Department of Chemistry, Director of the Michael Barber Centre for Collaborative Mass Spectrometry, located in the Manchester Institute of Biotechnology. She is also Associate Dean for Research Facility Development. Perdita is a world-renowned mass spectrometrist. She has authored over 160 publications, which have been cited over 4,000 times. In 2020, she initiated the COVID-19 Mass Spectrometry Coalition and was appointed as Chief Advisor to the UK Government on mass spectrometry as part of their pandemic response. She is especially well known for her work in Parkinson's disease. In 2021, Perdita founded the company Sibomix to exploit sebum as a diagnostic biofluid with a focus on Parkinson's disease. Here, she'll discuss how multi-reflecting time-of-flight instruments are advancing her research in this area. The Waters development and engineering team will be on hand to answer any questions at the end of the presentation, but you can submit questions at any time by clicking on the Ask a Question box. Okay, we are now ready to start the presentations, so I'll hand over to Jane. Jane, over to you.
Welcome to Waters Wilmslow HQ, and thank you for joining our webinar entitled Pushing the Boundaries of Science with Multi-Reflecting Time-of-Flight Technology. At Waters, we have a long history of innovation in mass spectrometry, and today it's my pleasure to introduce our next generation of QTOF mass spectrometer, the Xevo MRT. It's a fast, high-resolution, accurate mass spectrometer that delivers exceptional performance and speed without compromise. The Xevo MRT-MS is a next-generation benchtop QTOF, bringing together the high sensitivity of our robust TQ Absolute system in combination with the innovative multi-reflecting time-of-flight technology pioneered in the Select Series MRT. This combination is game-changing in making such high performance accessible to a wide range of users in a compact benchtop platform. The instrument developments that we have pioneered enable the Xevo MRT to be run at full sensitivity and full mass resolution, independent of the acquisition rate. The combination of performance and speed is unmatched by any other instrument, and we are very excited to tell you about this today. Today you'll hear about the benefits of 100,000 resolution at a lightning fast 100 Hz acquisition rate with less than 500 ppb RMS mass accuracy. This state-of-the-art technology delivers consistent robustness and reproducibility, generating exceptional data quality for research and routine applications. It's time to unlock a new level of confidence with an analytical powerhouse for every lab. Now let's take a closer look at the Xevo MRT, the product attributes and the technology that underpins its fantastic performance. I'll kick us off before I then hand over to Jason Wildgoose, our technical and engineering lead. Last week was a very exciting week at the American Society of Mass Spectrometry in Anaheim, California. We launched our next generation QTOF mass spectrometer, the Xevo MRT. This benchtop QTOF brings together the high sensitivity of our robust TQ Absolute system in combination with the innovative multi-reflecting time-of-flight technology pioneered in the SLEC series MRT. The instrument has incredible performance in a very compact footprint that's been designed to address the challenges that many scientists have told us about, including the comprehensive analysis of metabolites and lipids within complex matrices and the need to scale throughput for efficiency and productivity. Scientists want to acquire and process more samples in less time. Here's an overview of what we're going to talk about during the first part of the seminar today. I'll cover the performance attributes of the mass spectrometer, the resolution, the mass accuracy, speed, sensitivity, and informatics, before I then pass over to Jason, who will cover the technology that underpins the performance of the Xevo MRT. So let's take a look at the details. Here we list the 4 key attributes, all of which are critical. The headlining resolution specification is 100,000 on bovine insulin, the mass measurement accuracy is 500 ppb, MS acquisition rate is 50 Hz and 100 Hz in MSMS, and in terms of sensitivity, we achieve 10 times increase over the Xevo G3 QTOF at 30 Hz. So let's step through the product attributes further before we delve into the technology. Here we present the analysis of ubiquitin demonstrating the mass resolution of greater than 100,000, with mass resolution maintained in both MS and MSMS mode at all acquisition rates. This spectrum really captures the power of the mass analyzer. As an example of mass accuracy, here we see one channel of a DDA experiment processed in Skyline, demonstrating better than 500 ppb mass accuracy across 10 injections, with peak areas of 7% RSD without the use of an internal standard. The speed of time of flight affords a significant advantage when coupled to UPLC. Customers have told us that they wish to analyse more samples in less time, so the need for faster methods is key, and yet existing technology does not allow for further scaling. To highlight the performance and speed of the Xevo MRT, here we see tafenidine. The UPLC peak width at base is a little over a second. We have 52 data points and a mass resolution of greater than 70,000. To put sensitivity into context, here we see the results of a single-cell lipidomic analysis where a single THP1 cell was picked by fluorescence-activated cell sorting and analysed. The lipid highlighted is a phosphocholine. It's measured at greater than 80,000 resolution with a mass error of 380 ppb. Before I hand over to Jason, I want to cover a key additional attribute, the informatics pipeline, and how this provides our users with greater flexibility and convenience. The Xevo MRT is coupled to waters_connect software platform. Over the past year or so, we've undertaken a great deal of work to make waters_connect even more productive by developing applications such as sample submission, acquisition method editor, and LCMS toolkit. And putting this into perspective, these could be compared to the MassLink sample list, method editor, chromatogram and spectrum tools, adding familiarity and convenience. These new tools significantly aid usability and productivity, simplifying method development, data acquisition, and interrogation. We've also developed a new API that enables to link directly with software from Mass Analytica, such as Mars for metabolomics, LipiStar for lipidomics, and Mass Metasite for MetID. Further to this, we have a brand new app called Data Convert that can generate MZML files both at the point of data acquisition or post-processing, enabling the choice of and simplifying access to popular open source software such as MS-DIAL, MZMine, XCMS, and Skyline. That takes me to the end of the product attribute overview, and I'm going to hand over to Jason, who's going to take us through the technology behind the Xevo MRT.
Okay, thanks Jane. So I'm going to be using this instrument schematic. I'll work through from the source region to the acquisition system, so pretty much from left to right in this image. I'm not going to focus too much on the MS1 region, other than to say we've incorporated our latest source and quadrupole technologies as found on the TQ Absolute tandem quadrupole instruments, and we've enhanced this with our latest electronics control developments. This allows us to achieve tandem quadrupole-like levels of performance in terms of MSMS switching speed, sensitivity, and precursor isolation resolution. I will just give a quick example of the limitations that our latest electronics control developments can help us address. It concerns the issue of crosstalk when switching a resolving quadrupole between two different precursor ions, in this case between M/Z100 and M/Z710. As a quadrupole transitions, there's a short period of time, shown here around 5 milliseconds, when the quadrupole lets through unwanted ions over a wide M/Z range, which can lead to crosstalk or detector saturation issues. Whilst this effect is only short-lived, lasting maybe a millisecond or two, waiting for it to clear can lead to duty cycle limitations, especially at fast acquisition rates. The effect is a result of the synchronization between the quadrupole RF and DC voltages. In this scope trace you can see that the resolving DC lags slightly behind the RF, leading to a short period of time where the quadrupole is under resolving and lets through a wide M/Z range as shown in the previous slide. These types of MS1 synchronization effects have been addressed in the Xevo MRT, allowing faster MSMS switching rates. Now moving further downstream and taking a look at the collision cell and phase volume manipulator. These are new devices that allow us to efficiently capture and transmit both precursor and fragment ions. The collision cell design compresses the ion beam and allows high transmission through downstream apertures, maximizing sensitivity over a wide M/Z range. Importantly, the design also minimizes transit times through the collision cell. This allows the instrument to maintain the precursor isolation fidelity of the fast switching quadrupole I mentioned earlier. The PVM then efficiently transfers ions from the collision cell to the TOF, while simultaneously shaping the phase volume of the ion beam to ensure maximum resolution and maximum sensitivity at the same time, removing the need for separate resolution and sensitivity modes. The collision cell and PVM work in unison to provide simultaneous high transmission and resolution for both precursor and fragment ions. This image shows a simian model of the collision cell through to the orthogonal accelerator or OA of the TOF. Working from left to right, the collision cell compresses the phase space of the beam, effectively setting the initial conditions. The ions are then transferred to the PVM, which slightly expands and collimates the beam at a diameter of around 0.8 mm. This expansion and collimation is critical for reducing the kinetic energy spread of the ions in the beam. The vast majority of the beam is then transferred through a 1 mm aperture into the TOF OA for TOF analysis, where the aforementioned reduced energy spread leads to reduced turnaround time and higher resolutions. I'd also add that the PVM includes two multidimensional steering lenses that enables us to compensate for mechanical misalignments due to tolerances. The top image shows a similar model to the previous slide, but now with the gas cell and PVM misaligned by 0.5 mm. In this scenario, no ions make it through the 1 mm TOF aperture. A slight tuning of the steering lenses allows us to recover both the sensitivity and resolution of the system, as indicated by the bottom image. Okay, so I've shown that the collision cell PVM combination provides simultaneous high sensitivity and high resolution, but the other important attribute of the combination is speed. To give an appreciation of the timescales involved, here I'm showing data where the quadrupole is switched to isolate a precursor every 5 milliseconds, as indicated by the vertical dotted lines. This is an MSMS experiment, and we are looking at the time taken for associated fragment ions to reach the TOF. As we can see, the ion beam decays to 0 within 2 milliseconds, and it's this time scale that ultimately defines the interscan delays. This 2 millisecond interscan delay is significantly better than on our previous instruments, such as the Xevo G3 QTOF, which typically has a 14 millisecond interscan delay. The impact on duty cycle and therefore sensitivity of this improvement is shown in this plot. It highlights how the reduced interscan delay, the white space, allows us to maintain high sensitivity even at very fast acquisition rates. The data in green shows the Xevo G3 QTOF operating at up to 30 Hz, and the data in blue shows the Xevo MRT operating at up to 100 Hz, demonstrating that the Xevo MRT has significantly higher duty cycle than the Xevo G3, even when operating at greater than 3 times the acquisition speed. And finally, to demonstrate sensitivity versus scan rate, we ran a series of experiments infusing leucine and Kepler for 30 seconds at scan rates of 10 through to 100 Hz. 3 seconds of data were then combined to form the overlaid spectra. Zooming in on the carbon-12 isotope demonstrates the impact of sensitivity at varying scan rates. Here we show 80% duty cycle at 100 Hz, highlighting that we can generate data at high acquisition rates, maintaining high duty cycle and therefore sensitivity, all without compromising resolution. To understand how we achieved the resolution, we'll continue downstream and take a detailed look at the new TOF. As you can see, it's a multi-reflecting TOF with 8 reflections. To understand why these reflections are needed, it's worth taking a look back to the original TOF reference by Stevens in 1946, who pointed out that such a mass spectrometer should be well suited to rapid analysis, and it's easy to see why when you examine the fundamental equations that govern TOF-MS. Plug in some reasonable values and you can quickly show that TOF-MS spectra can be produced in tens of microseconds, which is obviously extremely fast. But what time of flight do we actually need to achieve our target performance? I showed previously that our gas-cell PVM combination did a really good job of transmitting the vast majority of ions through the 1mm TOF aperture with low energy spreads. For TOF-MS analysis, these energy spreads are converted into turnaround time using our state-of-the-art high-voltage pulsers that sample the beam in the OA. These turnaround times can be as little as a few hundred picoseconds for higher charge states. Combining this aberration with other instrument aberrations leads us to expected arrival time spreads of 0.4 to 0.6 nanoseconds, which in turn leads to a time of flight requirement of around 120 microseconds to achieve a resolution of 100,000. Similar calculations can be done for target mass measurement accuracies, or MMA, of less than 500 ppb. So in other words, we need to design a TOF-MS with a flight time of at least 120 microseconds to achieve resolution on our target sample. And of course, approaches to extend the flight time of TOF-MS have been well known for many years. The most common approach is to use reflectrons, or more broadly ion mirrors. The simplest example of this is the V-mode geometry shown here and found across a range of our products from over the years, such as the Xevo G3 QTOF and the BioAccord system. And you can add in more reflections by folding the V-mode flight path to give a W-mode geometry, as found on our higher resolution products such as the Select Series Cyclic IMS and the Synapt XS. And of course you can continue with this approach, but there is an important caveat. Adding in more reflections leads to more passes through the grids that define the different field regions of traditional reflectrons. And even though these grids can have high single pass transmissions at over 92%, the cumulative effect of many passes can cause significant loss in transmission and thus sensitivity, as shown here on the left. The obvious solution is to somehow remove the grids, but this is not a trivial task. The grids are there for a reason. They're there to support the reflectron fields to ensure that the fields are, to all intents and purposes, homogeneous across the dimensions of the beam. Simply removing them compromises that field support and can lead to significant defocusing of the beam, as ions with different initial positions and energies see different fields. Very few ions survive a single reflection, as shown in this extreme example, with the chances of surviving multiple reflections practically zero. To solve this, the mirror design must become more complex, with multiple electrodes of varying thickness and voltage combining to generate multiple focusing and defocusing regions within the mirror. These regions act to stabilize the ion trajectories, allowing multiple reflections with minimal losses. Applying this approach and repeating the video from a few slides back, we can now see that the ion trajectories are stable over multiple passes through the ion mirrors. Looking in another dimension shows the stable flight paths from the OA to the detector, and it's worth noting the red squares in this sim-ion model. The first red square shows when an ion is created. In this simulation, that equates to when ions are sampled by the OA. The second red square shows when an ion is destroyed by striking a surface. In this simulation, ions are only destroyed when they strike the detector. They strike no other surfaces, indicating extremely high transmission for ions sampled by the OA. Okay, so that's quite a lot of info, so it's probably worth a quick summary of the TOF. We've combined the best features of the Select Series MRT, those being gridless highly folded geometries, with the best features of our gridded TOFs, such as high duty cycle. These features have been coupled with a novel collision cell and phase volume manipulator that I described earlier. The result is a TOF with simultaneous high resolution and high sensitivity that is capable of very fast acquisition rates in a very small footprint. Last but not least, we've also made significant advancements in our detector and acquisition technology. The detector has an improved stability of response, ensuring reproducible results over time, and the acquisition system allows us to sample data at an effective rate of up to 60 gigabits per second. These kinds of rates are required because the inherent speed of TOF-MS, whilst largely beneficial, does pose some challenges. As you might imagine, if your separation time is of the order of hundreds of microseconds and you have high resolution, then individual peaks must be extremely short in time. In addition, they present over a range of intensities, placing some challenging constraints on the acquisition system. We have developed a novel solution using an ADC to sample the TOF data at 4 GHz and also provide some data reduction. These data are then transferred to a GPU for processing. And importantly, to deal with the wide dynamic range requirements, we have developed a dual gain amplifier that works in combination with the ADC and GPU. The approach splits the signal from the detector into two channels, one a high gain and one a low gain. The acquisition system is constantly checking the high gain data to check if it's too intense for the ADC to cope with. If it is, then those data are replaced by low gain data, with these data then rescaled by the GPU, leading to an acquisition system that in theory is capable of up to 6 orders of magnitude per second. So pulling these ion detection and acquisition improvements together allows us to demonstrate excellent reproducibility for lipidomics. Here we ran a batch of 500 injections of the EquiSplash standard from Avanti, acquired using the RAMP methodology. Processing the data using Skyline, we achieve RSDs across the 500 injections of around 6%, without the use of an internal standard or detector optimization. And finally, for the detection and acquisition system, we measured lipids as standards but also in human plasma matrix and demonstrated a linear response over 4 orders of dynamic range. Now before I finish, I just want to take a step back and look at the speed once again and highlight that TOF separation itself does not limit the speed of the instrument. Even when acquiring at 100 Hz, tens of individual spectra are being combined to form a spectrum. So we still have plenty of headroom before TOF-MS itself becomes a limiting factor from an instrument speed point of view. To finish off with a summary, the Xevo MRT incorporates our latest developments in MS1 technologies, allowing tandem quadrupole like MSMS switching speed, sensitivity and precursor isolation resolution. A new design of collision cell and transfer optic conditions the ion beam entering the TOF, minimizing the size and energy spread of our ions over a wide mass range, whilst keeping transit times to less than 2 milliseconds, allowing acquisition speeds of up to 100 Hz. Combining the best features of the Xevo G3 with the best features of the Select Series MRT enables simultaneous high sensitivity and high resolution in a small footprint. The latest detector developments enables robust and reproducible performance over extended timeframes with minimal user intervention. The new ADC GPU acquisition system allows acquisition and transfer of all the data without compromise. And as a final note, I would like to acknowledge the team who have brought this new instrument to life and thank our amazing collaborators. And thank you for your attention, and I look forward to answering any questions you might have. Thanks.
It's now my great pleasure to hand over to Professor Perdita Barran, who kicked off our Waters user meeting at ASMS just over a week ago. And we'll hear about how Perdita and her team are solving problems that matter.
Great pleasure to be here today to talk to all of you. It's really good to be able to tell you about the research we've done, and I'm sort of pretty thrilled to tell you about how that's been accelerated with some early access to the Xevo MRT. So probably some of you know that my group has been involved in trying to find metabolic markers for Parkinson's disease using an unusual biofluid that is sebum for some time. And those of you who know anything about diagnostics know that it's quite a hard journey, but recently we've had some good, promising results, so I'm getting a chance to talk to you about it. So let's first of all think why it is that we might need to diagnose Parkinson's disease. It's a progressive neurodegenerative disease, and it's the second most common age-related disorder after dementia. It's the fastest growing neurodegenerative disease globally. A lot of that is because we're getting older, and some of that is because there's improved diagnosis. But some of it is to do with the use of pesticides. In the main, Parkinson's disease is diagnosed after the motor symptoms that we all think of about it appear. And if we look at this image, If we look at this image here, we can see that by the time things are diagnosed, by the time we've progressed to clinical, the substantia nigra and dopamine receptors therein have been really damaged, sometimes to up to 70%. Whilst we think of it as a disease that affects old people, 4% of people that are diagnosed globally are under the age of 50. And for that age group in particular, and actually particularly for women, diagnosis can take up to 8 years. And what that means is those people are being unnecessarily treated. If you're stiff arm, one of the early symptoms, you stop swinging your arms when you walk, one arm becomes stiff. So you're then sent to have frozen soldier surgery. You may have gut problems, you may have sleep problems, you're put on sleeping pills, you're given gut treatment, and all of that is Parkinson's. That prodromal stage with those early symptoms can last up to, well, certainly up to 15 years. And our group and many others want to understand that progression and want to find markers for that progression to help with what we call timely diagnosis. At the moment, there are no drugs that could treat people pre-motor, but in development, there are neuroprotective agents. There's currently about 84 in development. And so being able to diagnose in a timely fashion will perhaps accelerate the uptake of those and our understanding of those. So there isn't a test available yet for Parkinson's disease, and this figure here shows the symptoms. I think the symptoms that are on the left-hand side are those that most of us associate with the disease, so that's the motor symptoms. But those on the right-hand side are things that, unless you know someone with Parkinson's, you'll probably be less aware of. I've already mentioned gut problems, sleeping problems. Pain is a really significant part of this disease. And then, interestingly, as you'll see, a loss of sense of smell. The diagnosis, therefore, is based on the observation of motor symptoms and taking a medical history. And there are different stages that have been developed such that we can start to have markers for progression as well, but this is all based on clinical observation. If you're an expert movement disorder specialist, your diagnostic capability is about 80 to 85%. So that means there is some underdiagnosis. The FDA improved a DAT scan in 2011, and that is useful, and there's been some wonderful new work in imaging contrast agents, but that's only really used in difficult diagnostic cases. It's expensive, and it's not always accessible to the individuals involved. There's been some very interesting recent progress with the use of seeding assays using pre-seeded alpha-synuclein, but that mostly relies on using cerebral spinal fluid, and that is not necessarily a biofluid that really we should be taking to try and screen for a disease. There has not been as much progress as certainly the Parkinson's community would like on defining observable testable progression markers and on early diagnosis. So I didn't want to solve all those problems. This lady came into my life. And she's called Joy Milne, and she had a very interesting story. Her husband was diagnosed with Parkinson's disease when he was young, so he was in that early, young onset Parkinson's disease cohort. But about 12 years before he was diagnosed, Joy noticed that he smelt differently. She told him to wash more. He was not very happy about this concept. And life carried on, and of course other symptoms came, and he was eventually diagnosed. Some years after that, she realized that all people with Parkinson's had the same odor. And she came to a colleague of mine who was giving a talk on his work on Parkinson's, and she challenged him to do something about this. She said, there is an early marker, it's the odor. What can you do about it? Well, he's a clinical biochemist. He really didn't know what to do at all. He looks at stem cells. But he rang me up and he said, Purdy, could you or could mass spectrometry diagnose or find a volatile? And I said, well, yeah, sure, but really? Do you really think she can smell disease? So we had to think about this a bit, and what we did was decide to have a method where she couldn't see the observable symptoms of Parkinson's, the motor symptoms, but she would be able to smell the odor. So we basically gave Joy some T-shirts to smell that had been worn by people with Parkinson's disease. We had 6 people who had Parkinson's disease, and we had 6 people who were control subjects. We cut them in half, so Joy actually had 24 T-shirts to smell. And she was entirely correct about the 6 individuals who had Parkinson's. Not only that, she was able to put the people back together. T-shirt number 12, that's matched with T-shirt number 16, that's the same person. It's remarkable. One of the T-shirts, which was in our control group, she said smelt of Parkinson's, and she grades from 1 to 4, with 4 being a very, very strong odor, and she said it was near 3. It was really quite strong. She was very definite about it. So false positive. Except it wasn't. That individual came back and told us 9 months later that he had just been diagnosed with Parkinson's disease. And so again, as she had done with her husband, she was able to pre-diagnose the disease before it had been clinically diagnosed. So that was remarkable. I cannot tell you how extraordinary it was to have this. You know, you just think, wow, someone can actually smell a disease and find it even when the person hadn't been clinically observed. Actually, the most remarkable thing about us using T-shirts was that we found out that the odor wasn't strongest in the armpits, which is what you'd think, right? You'd think it would be like that. It wasn't. It was in the area underneath the neck. And that's an area where we all collect a lot of sebum. We have it coming from our hair, and also, I don't know about any of you, but it's pretty difficult to wash, you know, that part of you, so you can sort of scrub. But anyway, it's rich in sebum, and that then led us to start to investigate this biofluid and to see what biomarkers we could find from it. So we set about to collect it and see if mass spectrometry could do what Joy could do and distinguish Parkinson's from control subjects. We've sought to develop a method to sample from people, and there's some images here from the sampling packs we send out to people at home, and then there's a picture there of the sort of pack that we send people. So we do everything in regular mail. There's no need for cold transport or cold storage, which is quite remarkable. We send Q-tips, wooden Q-tips, and we send gauzes, we send some gloves, and we send some jiffy bags for people to send the samples back to us. And we advise people to either self-sample their long-handled Q-tips or to get someone to sample from the mid-back. For thermodesorption gas chromatography mass spectrometry, we use gauze because it's a larger surface area, but we started doing that for LCMS, and we were using 9 mils of solvent per extraction, so we moved to the Q-tips, and they're actually much better, easier to use. We also sought collaborators, and I'm happy to say we have collaborators all over the world. We're involved in a very large study which is run out of the H.T. Chan Center in Harvard University with Cortese and Alberto Oshiro, and that's sampling from nurses in the US who have prodromal indicators of Parkinson's. So these are nurses who are just regularly sending samples into hospital labs all over the country, and these are the cohort who have suspect Parkinson's, so we're looking for them. We have samples from all over Europe, and we're also involved in a very large study that's sampling people from 10 sub-Saharan African countries. Our current findings are this: with thermodesorption GCMS, which is most similar to smell, right? We find about 600 volatiles on everyone's sebum, and about 5% can predict PD now with 97% sensitivity. There is a prodromal, very likely prodromal form of Parkinson's called REM sleep behavior disorder, and that has a different volatile signature, and we found that. With LCMS, using different platforms, we find about 25,000 features, and about 10% of those are significant for different differentiation between Parkinson's and control. We never thought, but we were able to do some really detailed pathway analysis to learn about the pathways that are disrupted during the disease, and there's substantial lipid dysregulation and alteration of the carnitine shuttle. We've also used paper spray coupled with eye mobility mass spectrometry, and we can really now see some very, very long lipids that are substantially upregulated in people with Parkinson's disease, and that's a very fast assay. One of the cohorts that we've been working with a lot is based at Oxford University. It's been there for more than nearly 15 years now. 1,000 people were recruited, and they've been followed up at regular intervals. There's very good matched controls, and there's also a large cohort of people with REM sleep behavior disorder, which is a condition where if you had 100 people, within 10 years, 75 to 80 of them will have converted to Parkinson's. So the conversion rate is about 8% a year. And there's also relatives to study. In the work I'm going to show you, we've taken a subset from this well-studied cohort, 76 samples with Parkinson's, 78 with RBD, and some matched controls. We mostly, for this, we sampled these people at home. We sent the sampling packs to Oxford, and they sent them on to them, and we're blinded to it. And this is led by Michelle Hu at Oxford. We increasingly look to my predecessor at the Michael Barber Centre at Manchester, who some of you may know, Simon Gaskell, to think about the way we approach analysis. I think one of the great things about omics and mass spectrometry and everything is how many features we find. But actually, you talk to a clinical mass spectrometrist and they want one qualifier, one quantifier. So what is the point of having all those lists of metabolites and all those lists of proteins? Actually, we want robust features that can be measured again and again. And so what we've done with the Xevo MRT, it was very kind of coincidental because this was the way we were thinking too, is to think about shortening the runtime and seeing how much information we can get. We've also run a subset of those samples on a IMS cyclic because we've seen separation with eye mobility for some of the isometric and isobaric lipids, so it helps us to do that. And then we've looked at the features generated using a conventional progenesis-based pipeline and also a new faster, robust pipeline. We've then built a predictive model and translated the markers for targeted MRM. So Simon had a very useful way of thinking about this sort of approach, which is shown here, just enough diagnostic information. Right? This is really what we want, and it's what we want out of the way we do things generally and what we've done with the MRT. So here's lists of the different chromatographic conditions we've taken. So our conventional metabolomics on the cyclic is a 22-minute gradient using a Acuity I-class. And then on the Xevo MRT, we've taken what we call routine. That's what Lee Geppings, who was really instrumental in doing this, he said routine. I was like, wow, if routine is 12 minutes, we're in good shape. And then high throughput, which is 7 minutes. And the really important thing about these shorter run times is that that's the sort of runtime you'd put onto your triple quad assay, right? So any chromatographic conditions that you develop, you can translate more quickly. Same solvents in all cases. Here's just showing a bit more detail about how we do those gradient profiles. So there's a bit to just try and push the lipids out. And we've already learnt something about this instrument, but just to tell you, all the data I show you is positive mode electrospray. We've got the opportunity to have two different scan rates, one at 10 Hertz, which is what we use in the routine, and in the high throughput, mode, we're running at 20 Hertz, which is pretty amazing when you consider that 4-meter iron path they're going through. Collision energy ramp and source and sample conditions as shown there. Something that hasn't been mentioned is it's really quite wee, this instrument. It's really not very big, and you know, that's a nice thing, and you see it there in profile. So here's some comparator chromatograms. This is our conventional cyclic 22-minute gradient. This is the routine on the Xevo MRT, and then this is pushed to the 7-minute. And these are all rich with diagnostic features. And why are we doing this? Because you want to get things done quickly, particularly if you want to take this to screening or to some sort of targeted approach. The mass spectrometry data from this instrument is pretty remarkable. So this is a triglyceride lipid from slightly late, and this is in the routine chromatographic run. It's about 12 minutes, and that's coming through at about 8.5 minutes, and that's a representative lipid that we see. And even when we go to high throughput, now at twice the frequency, so if you can see the intensity, it's a teeny bit lower, but not really. I mean, sorry, it's higher because we're sampling twice as fast, but it's really commensurate, and the mass resolution isn't compromised at all when we do that, which is pretty remarkable from a small instrument that's working pretty fast. So we can compare the peak capacity that we get with our cyclic, around about 55, and the resolution we get there on these sorts of samples is about 45,000, with that we're getting with the MRT. And you can see there's a significant improvement in all cases there, even on that 7-minute gradient, so about a third of the speed. So we've taken two ways of processing, like, you know, let's take some really interesting samples, put them on a brand new instrument, and let's just use a different processing pipeline too. But that's reaped some pretty good results. So we've used the routine progenesis approach, where we take the data, deconvolute, de-isotope, do alignment with QCs, peak picking, and then identification with statistics. We've also taken a novel method, working very much with Hans Vissers at Waters, which takes different modules out of the progenesis pipeline, but is very much faster, and to an extent is signal agnostic, not signal agnostic, but data agnostic, and allows us to really pull things through much more quickly. In the end, also using R to generate models for prediction. So here's just an example of some of the data we get from cyclic. This is LCMS data deconvoluted with progenesis QI. Do all of our peak picking and alignment and area normalization, and this takes quite some time, and all of our samples are referenced to pool QCs in both cases. You can see these are rich data sets, and that's not even looking at the arm mobility data with, as I've said already, around about 2,400 features. We then take features that are absent in more than 10% of the QCs out, and take those where we've got big variation in QCs also out. This leads us to around about 12,500 features, which we then are able to robustly detect throughout. Some of those features are a particular interesting thing of doing sampling where we sample. Anyone want to guess what those are up there? Because they're sort of things you've probably seen before. You get them more with women, it's shampoo. So we see that coming through, but that's okay, that works as quite nice markers. So we also have applied progenesis methods to the new data, but I'm not going to show you that at the moment. But the modular pipeline is producing similar sorts of sample numbers, so from total features and then down to scaled features. The difference in the two numbers there is this was us looking from 50 to 2,000, which is what we tend to do for our cyclic data, and this is looking just up to 1,600, which is more commensurate with what we did on the MRT. And you can see there that even with those shorter run times, we're still getting an enormous number of features. And just to remind you all, we've taken a Q-tip, it's been rubbed on someone's back, and we're analysing it, and we really do have a lot to work with. We then take those features and start to cluster them, and you can see there's some pretty good clustering going on, and here's an example of some of this is just doing leave one out to look at the robustness of features. And in this was based on cyclic data actually, we built a model based on 3 features, which gave us, and that was only a subset, it was only 15% of those 200 samples we run there, which gave us fairly good confidence. We then reran that on the MRT data, and we have very good predictability. So on a test set, we now, based on this sample size, we have 88% sensitivity with what we've achieved. So we were pretty pleased about that. It's great when you do things on 2 discovery platforms, because you can go and check that you've got the same feature, and indeed we do. So the data here is showing data from the cyclic data from the cyclic is at the bottom, and data from the MRT. You can see there's a little bit of crossover there, but of course we can pull out those features, and those were enough for our predictive model. So top 7 was enough for that predictive model I just showed you. And this is then transportable for Skyline for targeted assay development. So what's the prospect of using this for a test of clinical utility? That's why we're doing what we're doing. Well, I've shown you that sebum is a very rich source of diagnostic biomarkers. The sampling is just non-invasive. It's really incredibly easy. And actually, we all got used to that sort of thing with COVID, but it's a lot better doing that than shoving something up your nose. It can be done at home, and samples can be transported and stored under ambient conditions, which is really helpful. All of this, and anyone working in translation of clinical omics to anything that's going to be useful, needs to work along with clinicians, and we do that a lot. Our ability to reduce any false positives or false negatives increases dramatically if we have clinical markers, and we do. So what I've shown you is our ROT curves for just the mass spectrometry data. If we add in one of the markers that we know clinically of those people, then we have pretty much 100% accuracy. Our aim is to work to stratify this disease and how it progresses, and to use biomarkers to inform clinicians and improve the outcome for patients, particularly at the early stages, but also as the disease progresses. We think that there's a really good opportunity, as I've told you before, to use this method along with trials for neuroprotective agents and other therapies for at-risk groups, so people who have familial or genetic risk of getting Parkinson's disease. Being able to translate to an MRM method for clinical biochemistry labs, because that's what they use triple quads, is really facilitated by taking this sort of approach. And in our hands, it's been really facilitated by access to the Xevo MRT. The great thing, as I've mentioned, is that we can map that discovery gradient right onto the targeted gradient. And this new pipeline has allowed us to rapidly assess putative features. I think an approach where you take 2 discovery platforms, you run the same samples on them, and then look for features is got to be the way forward. And we found it pretty exciting to be able to do that. Just to acknowledge, there's Joy and Les, who's no longer with us, but that was them in happier days, and a lot of the clinicians that we've worked with, and you for your time. Thank you very much.
Thank you very much, Jane, Jason, and Perdita, for sharing your expertise. Okay, so we're now ready to start the live Q&A session with the Waters Development and Engineering team. We're pleased to have Lee Gethings with us. And we'll try and get through as many questions as we can. So the first question, what is the acquisition software that's used to control the Xevo MRT, Waters Connect and/or MassLynx?
Okay, so I'll take that one. I'll kick us off. So the Xevo MRT is on the Waters Connect software platform. And actually over the last year or so, we've undertaken quite a lot of development on Waters Connect in terms of adding additional applications. So we have the sample submission app, the acquisition method editor, MS Toolkit, data convert, and these are all part of the Waters Connect package. And they're similar in a way to like the MassLynx setup in terms of having a sample list, the method editor, the chromatogram and spectral tools that we have. So it's really improving the usability for customers in terms of setting up experiments, interrogating data and processing data. So yeah, Waters Connect. Okay,
great. And how many valves are present behind the fluidics door? Is the lock sprayer still used for real-time mass accuracy checks?
Yeah, okay. So I'll pick that one up. Yeah, we don't actually have a fluidics door in that sense. It's different to what we've done previously. The fluidics is an option on this instrument. So we do have one integrated valve, one integrated divert valve on the instrument, and then within the optional fluidics we have a second valve and a pump, and those are there. Yeah, to the point that's raised there. Yeah, those are there to drive the lock spray, which is still the best way to get mass accuracy on this instrument.
Is the DESI XS available and compatible with the Xevo MRT?
So DESI XS is not available on the Xevo MRT, but obviously is available on a range of our HRMS platforms. So for example, the Select Series MRT, Select Series Cyclic, the Synapt XS, and also we've got entry-level option of a DESI with the Xevo G3 QTOF.
Okay. A couple of questions here on the time of flight. Is the time of flight analysis multiplexed?
No, it's not on this instrument. So the multiplexing option that we developed on the Select Series MRT was to deal with an inherently low duty cycle. So to recover that duty cycle, the duty cycle of this instrument, the inherent duty cycle, that's the TOF sampling duty cycle of this instrument, is 2 orders of magnitude better than the Select Series MRT to start with. So we don't have to do that. We don't have to apply that technique to recover the duty cycle in the first place. It's already high.
And can you adjust the number of TOF reflections?
Yeah, I've been asked that before. In principle, yes, you can. However, it costs you something. So when we talk about I just mentioned the OA duty cycle, that's to do with the shape of the beam coming out of the OA. If you change the angle of that beam coming out of the OA to either reduce the number of reflections or increase the number of reflections, you end up clipping the beam somewhere. So in principle, you can, but the instrument isn't optimized for that. So I wouldn't advise it.
Okay. What is the loss sensitivity when you increase the speed of acquisition in MSMS?
So again, as I showed in some of those slides earlier, we've got a very fast switching quadrupole now on this instrument, which allows us to switch between different precursors in less than a millisecond. The gas cell transit times maintain the fidelity of that sort of fast switching, and those sort of the change, you see the change in the data at the top, maybe, well, as I said, less than 2 milliseconds after the quad switches. So we traditionally have we effectively have a period of time of about 2 milliseconds where we don't collect data. So what that translates to when you're talking about sensitivity losses, you have a 2 millisecond overhead. So at 1 hertz, that corresponds to, if you're looking at 1 spectrum per second and 2 milliseconds of it is dead, that's 99.8% duty cycle. And at 100 hertz, that corresponds to 80% duty cycle. So switching from 1 hertz to 100 hertz will cost you about 20% in terms of sensitivity through the duty cycle effect.
Okay, great. So what source options and fragmentation technologies are available on the Xevo MRT?
So in terms of source options, we have electrospray, APCI, and nanoflow. In terms of fragmentation, it's CID, collision-induced dissociation. But I think one of the questions was around alternative fragmentation. So what I would say that we have that available again across a number of products in our portfolio. So with the Select Series product, we have collision-induced dissociation, SID, and ECD, so electron capture dissociation. And then on the Synapt XS, we have electron transfer dissociation, so ETD.
Brilliant. And can the Xevo MRT collect DIA data like sonar and or MSE? If so, which ones? And can you comment on the observed performance?
Yes, so the options we have available is the MSE functionality, so that's our DIA, data independent acquisition. We also have DDA and MSMS.
And is the IDC intelligent data capture function for lowering data file sizes available on the Xevo MRT?
Yes, definitely. So that's within the Waters Connect software platform and within the driver. So the intelligent data capture algorithm, it basically reduces the noise in the data, and it is what it says. It's intelligent. So if it sees noise, it will remove it. But if it sees something like a peak, and when I say that, I mean if it's tracking as a Gaussian profile, it will see that as a real entity, and obviously not interfere with reducing that. It's just removing the noise.
So this next attendee asks, we're seeing lots of data strategies for metabolomics/omics. Where or how does the Xevo MRT fit?
So I'll take that one. So we've got multiple options available from Waters Connect. So we can either take the API route into software packages such as those from Mass Analytica. So that includes Mars, LipoStar, and Mass Metasite as well. In addition to that, we also have the flexibility that is offered by Data Convert. So this allows us to take our data file format into MTML formats, and then we can use that in multiple third-party informatic solutions. So anything from XCMS, Skyline, MZMine, multiple third-party solutions. So again, we've really got flexibility. So again, we can either use Data Convert or the API route. So both options.
Okay, brilliant. So maybe a good question to close on. So what's next for multi-reflecting time-of-flight technology?
Okay, I can answer that, I guess. So yeah, we see as an organisation, Waters sees multi-reflecting soft technology as a core tech now within Waters. The inherent speed that we've described in these presentations of all TOF analysis, but MRT TOF analysis as well, combined with the high resolutions we can now achieve and the high sensitivities all simultaneously, clearly make that technology applicable to a wide range of applications. So we, as I've just shown today, we foresee a role for it in lipidomics and metabolomics, as I say, as we've discussed today, but also in areas like biopharma and proteomics. We'll be looking at those in the future at some point. So yeah, watch this space.
All right, brilliant. Well, thank you, Jane, Jason, and Lee for answering those questions. I think that's all we've got time for today. But don't worry if your question hasn't been answered here live, because we will pass over all the questions to our speakers so they can follow up via email. If you wish to revisit any of the topics covered today, this webinar will be available on demand in the next couple of days. So thanks again to our speakers, and thanks to everyone for attending. I look forward to seeing you at future webinars.